All right. Hello, everybody. Welcome to Cloudflare. This is our 5th crypto meetup. We've been doing it for over 2 years, and this is just a good way for us to come around to Cloudflare, meet other people who are interested in cryptography and cryptographic applications, and just take a look at what people are doing, what interesting things are happening in the field. I'm very happy to introduce our first speaker, Deirdre Connolly, who will be talking about post-quantum cryptography. So everyone give a nice round of applause for Deirdre.
Hello. Hi, my name is Deirdre. I'm a software engineer at Repo, and today I'm talking about super singular isogeny Diffie-Hellman. And this is a proposed post-quantum key exchange crypto system. It's a lot of words, but who here has heard of quantum computers? I'm in San Francisco. It should be a lot of people. Who has heard of post-quantum crypto before today? Yay, cool. All right, cool. So as some of you may be aware, quantum computers are coming, whether it's 10 years or 10 years after that. They're going to come along, and when they come along, it's not clicking. Help. Yay. This guy is going to come and eat our lunch. So this is Shor's algorithm in a terrifying personified form. He will, when quantum computers come around and we can run this algorithm on them, he will break all of our currently deployed asymmetric cryptography. That's your RSA, that's your signatures, that's your all the key exchanges that we currently have, and this makes us sad. We need to start working on post-quantum crypto now so that we can deploy it in time for when this guy comes to town. It took us almost 30 years from the first paper on elliptic curve crypto to get it deployed widely for consumer software. So we need to start now to be prepared for that future, but also we need to be prepared before the day that quantum computers come online, because you can record everything that we are sending now that depends on asymmetric crypto for its security. So you can record TLS traffic and other things, save them in a database somewhere, and then when you have a quantum computer handy, just decrypt them and see if anything handy was in there. So there is an urgency to find new post-quantum key exchanges in particular that we can deploy sooner than later. So what do we have for key exchange right now? Key exchange, especially when we use it in TLS, which is what we use to encrypt our traffic over the web via HTTPS, which is now 50% of web traffic and rising, which is great, is a way for two parties who have never communicated before to agree on a shared secret over a public channel. So usually how this works is you have some common parameters that everyone understands who speaks this protocol. You generate a secret on your side. You combine your secret with the public parameters, swap them with the peer you want to communicate with, do another computation involving their public key, your secret, and you get a common shared value. And you can use this as your symmetric crypto key, like you can use it as the key for a block cipher like AES or other things. So when this was first proposed in the 70s, everything was integers. It was all over a finite field. So all the numbers involved in the computations between 0 and almost a prime number. And everything you sent over the wire was an integer, and all of your public keys and your private keys were integers. And that worked fine for a while until computers got faster and attacks got better, and the keys had to get bigger and bigger and bigger to maintain their security. So in the 80s, elliptic curve cryptography was proposed. And instead of having everything over the integers, you would use an elliptic curve that everyone understood, and the solutions to this equation, a polynomial that we like called elliptic curves, as your public key, and then you would do some computations and you would both arrive at a different point on this curve, and that would be your shared secret. But, unfortunately, all of this is, being stalked by Shor's algorithm. So why elliptic curves? Well, elliptic curves are nice because unlike any other random class of polynomials, if you take all of the solutions to an elliptic curve equation, all the points that make up the curve, and a little hack called the point in infinity that we use as an identity point, you get an abelian group. And abelian groups are great because that is what we were using when we came up with Diffie-Hellman in the first place and just did it all with integers. One thing that's different though is that with integers, you can add them together and multiply them together. With elliptic curve points, you can add them together, but you can't multiply a point by another point. That just doesn't work as a group operation. And this is kind of a hint to why elliptic curves are more secure and we can have smaller key sizes. So that's one reason we like elliptic curves. So what can we do with the curve as an abelian group? You can add a point to the identity point and get the point back. You can add a point to its inverse and get the identity point. You can add a point to itself, and the way you do this is you take the tangent at the point, find where it intersects up somewhere else on the curve, because by definition it must intersect at a third point, and find the reflected over the x-axis, and that is the result of a point plus itself. So that little purple one down there, that is the result of 2p. And when you add a point to itself multiple times, we call this scalar multiplication, because you're not actually multiplying the same elements that make up the group. You're multiplying the elements of the group at the point by another value. We call it a scalar. So if you add a point to itself enough times, you might come back to the identity point. And the value that you multiply the point by is called the order. And when you do this, you run through a whole bunch of points on the way from the point that the generator point all the way up to the identity. And we call this, this is another subgroup, this is another group, and we call the point that generated it, in this case P, the generator point. So these are some nice things about elliptic curves that are very useful for the elliptic curve crypto that we have today and will come in handy later. So we started with the integers, we moved over to elliptic curves, but we can't really use this anymore, and that's really unfortunate. One thing that's unfortunate about losing elliptic curve crypto is that it's only been around for cryptography for about 30 years, but it's based on a very wide, deep body of pure math analysis. We know a lot about how elliptic curves work and their properties and all sorts of things we can do with them, and it would be unfortunate if all of that was thrown away because of Shor's algorithm. So one proposal is instead of sharing integers, instead of sharing points on a curve, we generate whole new curves on the fly for every key exchange and swap them with our peer. And then we do some computation and agree on a shared secret curve or a shared secret curve value. And this is how we do supersingular isogeny Diffie-Hellman. So what is an isogeny? Because it's a weird word. An isogeny is just a map between one elliptic curve to another, from a pre-image curve to an image curve. What we're actually doing is you can put every point that makes up the pre-image curve through a transform and get another point on the destination curve. And this works for every point in the pre-image curve, and it goes to some point that does exist in the destination curve. And this includes the identity point. You will map the identity point on the pre-image curve to the identity point on the destination curve. This might seem kind of vague and abstract, but we've already seen it. Inversion is a valid isogeny. Scalar multiplication that we just saw is a valid isogeny. It just so happens that the pre-image curve and the image curve are the same curve. This is handy to see, and that it works for the identity point. And it also has this nice property where it's commutative. So if we do a scalar multiplication of an image point, say an image of the identity, it's the same value as if we took the image of the scalar multiplication of the identity. This works. It just comes out correctly. It doesn't have to be the identity point. It can be another point in the curve. So these are some nice things that we can use with isogenies. But we're not going to use it, we're not going to do it from a curve to itself. That's what we were already doing for elliptic curve crypto. Oops. So for post-quantum crypto, we're not going to use simple isogenies like that. We're going to use isogenies that kind of look like this. This is called a high degree isogeny. And this one has degree like 372 or something like that. And the reason we want to do this is because if the degree of the isogeny is smooth, aka it's not a prime, and it can be composed into many, many, many small primes, like 2 and 3 and stuff like that, we can put that together by computing a whole bunch of little isogenies, which are easy to compute, and composing them all together. And the way we do this is we start at a base curve, and then we compute a small degree isogeny, like degree 2, from base curve to another curve. And then we compute another curve from the second curve to a third curve, from the third curve to the fourth curve. And we basically chain them all together. And when you chain them all together, you get that high degree isogeny. Why do we want to do that? Well, it turns out that doing this is equivalent to a random walk in an isogeny graph. So in this graph, we start at E, and all of these nodes are different elliptic curves. And all these edges are small degree isogeny. So this is equivalent to a 2 isogeny graph. So when we chain together all those isogenies, when we compose together those low degree isogenies in order to create a big one, we're basically taking a random walk in this graph. In order to find the isogeny from, say, E to E prime, we have to walk this graph, we have to walk the graph from E, and we have to find some path between them. Shor's algorithm is not good at solving this problem. So this is a nice mathematical problem that we can use to prevent against attacks by Shor's algorithm. There is an algorithm that is around that kind of hurts. This is Grover's algorithm. He's scary, but not too scary. And what Grover's algorithm does is it's usually heard in the context of attacking symmetric crypto, so AES and stuff like that. It basically turns what would normally require a full brute force search and provides a root n speedup. So if you had to search n items in classical terms, Grover's will let you search root n terms. And that's okay, because then we can just double our key size in terms of AES, and we can double our graph size in terms of isogenies. So given that, the best known classical algorithm against SIDH like this is about p to the 1/4, and there is a optimized attack that uses Grover's algorithm as part of it, and that is order p to the 1/6. So for p, all of the isogeny stuff that we just looked at, all of the arithmetic is done over a finite field. It is all mod a prime. And so in this case, our prime, if we wanted 128 bits of quantum security, we have a prime that's like 768 bits. And that's totally fine. Cool. So we're going to talk about the actual protocol to do key exchange with isogenies at a high level, and then I'm going to go into the details after that. So everyone agrees on an elliptic curve, E. Everyone agrees on a prime. And then both parties compute a point that acts as a generator of a subgroup, and it's secret. You hold the point secret. The way it's implemented in practice is you have a secret number, and you're using that to compute this point. All of the points that Alice will use and all of the points that Bob will use are in different subgroups of E. So Alice should never pick the same secret point as Bob, and Bob should never pick the same secret point as Alice ever. And using the secret point and the subgroup that it generates, you're able to compute a unique isogeny. So you put the base curve that everyone knows about through this isogeny, and you get a public curve. So this is generated on the fly every time you do a new key exchange. So Alice will send her public curve EA to Bob, and Bob will send his public curve EB to Alice. Now we compute a new isogeny, and we do this there's some extra information that's getting sent along, but effectively what we do is we're able to create another subgroup that uniquely defines a new isogeny that is effectively our secret point that we used originally transformed by Bob's secret isogeny, and vice versa. And I'll get into the details of that in a second. So we create one more isogeny, and then Alice puts Bob's public curve through the second isogeny to get a new curve EAB, and Bob puts Alice's public curve through his new isogeny to get EBA. Now, what's interesting here is that unlike finite field Diffie-Hellman, unlike elliptic curve Diffie-Hellman, which at the end of like their last Diffie-Hellman-ish step, they come out to the exact same value, these curves are not exactly the same. Like if you wrote out their equations, they would have different coefficients. However, they have the same J invariant. So you can take those coefficients, like y squared equals x cubed plus ax plus b. You take a and b and you stick them into a formula, for both curves, they come out to the same value. And that is the value that we use as our secret key, as our shared secret. And then you can, use it as a symmetric key or whatever you want to do with it. Okay, cool. So we're going to go into details from Bob's perspective. When we set up the protocol, we set up a couple of values, including E, before everyone starts to know how to communicate. So for elliptic curves, everyone agrees on a curve and a generator point on that curve. So curve 25519, stuff like that. So in this protocol, we have a curve, a prime. In this case, it's over an extension field, but whatever. In this case, this is a super singular curve. This is not the same kind of curve that we use for elliptic curve crypto today. And the reason we use a super singular curve is because there is a quantum attack, a quantum sub-exponential attack against the same key exchange, but using ordinary curves, using the same kind of curves that we use today. And so in this case, we just swap out an ordinary curve to a super singular curve, and it looks like this. And then we define two pairs of points, PA and QA for Alice, and PB and QB for Bob. So these 4 points are known to everyone who can speak this protocol, including any malicious people who are listening in. All of these things are known to everyone. PA and QB, and their respective for Bob, are generator points of a subgroup that lies in E. So what that means is that these 2 points, when you combine them in any sort of fashion, you just can do P plus Q or P plus NQ or N plus P, NP plus Q or something like that. All those possible combinations will generate the whole subgroup of points that all have the same order. In this case, for Alice, they have 2 to the 372 order, and for Bob, they have 3 to 239 order. These numbers are chosen so that the orders are approximately the same for like when they actually add up, but they're different subgroups for Alice and Bob, so that they're always choosing points from one subgroup and not the other for their peer. Okay? So when you compute your secret isogeny, like the actual secret key, as I mentioned, you do a linear combination of your points. So all of this is from Bob's perspective. So you take your basis points of your special subgroup and you do a linear combination. So you pick some secret scalars from between 0 and P, our special P that we picked before. And this just lets you pick a random point in your subgroup, and you know that every point in that subgroup has the same order and has a large order. And what we do is, because you can use this point as a generator of another subgroup, we use that subgroup as the unique identifier of an isogeny between E and a new curve, EB, in this case for Bob. And the way that works is that a kernel of an isogeny is all of the points in the pre-image curve that map to the identity point in the image curve. And this is a unique way to identify an isogeny. Okay? And that's what that notation means. So we put the base curve through our new isogeny, and we send it over to our peer Alice with some extra information. So not just EB, but the image of Alice's basis points. So PA and QA are Alice's points, but we're putting them through our secret isogeny and then sending the results over to Alice. The reason we need to do this is because we switched over to super singular curves. When we're using ordinary curves, there were some nice properties of ordinary curves that we didn't have to do this, and we didn't have to send this extra information because we had some nice commutative properties, but we got rid of those commutative properties because they resulted to a quantum attack. So we have to send this extra information over. So this, the EB and the 2 points that we've transformed, are the public key. This is about 550 bytes when you send it over the wire. Okay. And then Bob receives Alice's equivalent, her public curve, and her transformations of Bob's basis points. So all this information is public. Now, this is the cool part. We take the same secret values, the secret scalars that we used to generate our private point, our secret isogeny generator earlier, and we do the same combination, but with Alice's public points. So what this does is it actually works out to be the same value as if Alice magically had access to our secret point and put it through her secret isogeny. So when we generate RB prime, it is directly dependent on the secret value that we generated and the secret value that Alice generated. And so we're able to generate a new isogeny that is directly dependent on our secret value and Alice's secret value. And then when we transform Alice's public curve through this isogeny, we come out to a new curve. And as I said before, these curves have the same J invariant. That means that they're isomorphic. These curves are directly dependent on Alice's secret value and Bob's secret value. You have to basically do a linear combination of these two secret values, generate a subgroup, and that is how you can get from E to the final shared secret curve. That's most of the nitty-gritty. This is basically how it works in practice. You can make some optimizations about how you represent points on the wire. You can just send an X coordinate, or you can just send a J invariant of a public curve or something like that. But this is how it works under the covers. Cool. This sounds really neat. I think this is really cool. Why don't we hear about this more? Well, post-quantum crypto is a diverse field. There are a lot of problems that we're looking at to see which ones are secure and usable when we need them. So lattice-based crypto has gotten a lot of attention and is strong contender for kind of key exchange stuff. But we don't just have to do key exchange stuff. We have to do signatures, other things. So we have different problems that we want to look at, as well as the fact that we want a diversity of problems, so we don't put all our eggs in one basket. So there's only been about 10 years of isogeny-based crypto research, quantum secure isogeny-based crypto research. In the past 10 years, there's been on the order of 10 papers on ePrint, which is a public publisher of cryptography papers. And so, isogeny crypto has been a little fringe for the past 10 years. So like Dan Bernstein did a talk about over a year ago, where he's like, oh, there's some people working on isogeny crypto and it's very exotic and not enough people have looked at it and no one knows how it works. And until the past year, that's been true. In the past year, there's been a flurry of activity of isogeny-based crypto. There's been 13 papers in the last year alone on that same preprint looking at isogeny-based crypto, trying to improve it, trying to establish firm boundaries on how secure it is or isn't. One of the most exciting papers was by Microsoft Research, where they were able to apply very common high-performance elliptic curve crypto techniques to this SIDH problem, to this SIDH protocol, and they were able to get some great speedups. They were able to get 200% speed up over the previous best record when they implemented just C, and they just ran it on just like a Haswell processor. So this brings key exchange down to about 50 milliseconds of compute, not network time, but compute time. And that is with a 550 byte public key. They've also done research where they're able to compress the public key, but you get 100% overhead on the compute time. And they've also done some work on how you validate your public key. Like when Alice sends you a curve and some points, how can you make sure that that is a legitimate curve that you can reach from the base curve and the points are valid and things like that. This is quite relevant because in December, there was an excellent security-based paper by Galbraith and his co-authors looking at the security of the problem. One of the nice results that they found was that if you can compute that shared secret, you can split it up. You can basically take half of the shared secret and use it for a MAC key, and the other part you can use for the actual key for AES or something like that. So it was secure to do that. But the big flashy result that they had is an active adaptive attack against a static SIDH key. So if people are aware of how you deploy key exchange on TLS, for example, we really like ephemeral keys. We don't want you to keep the same key lying around for a long time We want it fast and efficient so that we can have a new key every time. So that if that key gets compromised, you can just compute a new one, and all of your forward traffic is secure, and all of the traffic in the past is secure. Unfortunately, sometimes in the real world, keys hang around, even if they're supposed to be ephemeral, and sometimes they get reused across multiple connections. This attack basically showed that if they can leak some data, so for example, if they did a key exchange and they know what the right key is, but they changed a little bit of something and they were able to find what the wrong key is, they were able to detect bit by bit by bit with multiple key exchange attempts against the same static key. They were able to unveil the entire shared secret. And one cool thing is that this was implemented this past weekend in a capture the flag as a high level challenge. They actually, they used the Microsoft researchers code, which is available as a patch for OpenSSL, which is really cool. It's really nice, by the way. They stood that up and they asked people to attempt this active adaptive attack. No one did it. They did it though. The guys who ran the challenge actually implemented it, and they were able to run and get the whole key in less than 30 minutes. So SADH, bad for static keys. However, we kind of have this problem in the real world too. Like, we have to be able to have timing attack proof, cache timing proof, leak proof code, because there are some attacks against elliptic curve Diffie-Hellman and finite field Diffie-Hellman that let you reveal real bits of your secret if you make multiple attempts or even a single attempt. So one of the important things is we need to be able to validate the public keys that are getting shared with us. And unfortunately, all the techniques we have for SADH are kind of slow. They're not worth it. They're really bad. But they also require you to compute over the malicious shared point in order to verify whether it's a malicious point. So you may actually leak information while you're trying to prevent leaking information. So this is an open problem for SADH, and hopefully we'll see more progress on this soon. So here are some links to these papers. You can't click on them here, but you can Google them. They're all available for on the open web. The first paper is the 2011 seminal SADH paper that actually made people kind of stand up and pay attention and see it as a key exchange competitor. The second one is the Microsoft paper that made things really fast. And the third one is the recent security paper from Galbraith and his co-authors. Yeah. I think the world needs more isogenies. I don't know about you, but thanks. Questions? Time for questions? Okay, we have time for a few questions. Do you have any questions? Yeah. Yep. We don't care because the security of the problem is based on the map between the two public curves. Super singular curves are not used because the discrete log problem and finding subgroups in those curves is really easy. And on top of that, the curves that we use for SADH, they have a smooth order. They don't even have a prime order. So like all of those things are used mostly for performance, but there are other specific things. But we do not care about the discrete log problem in this case. The security is completely based on the hidden isogeny problem, basically. Sometimes there are some validation techniques that compute the discrete log to make sure that something is right. So we don't have to worry about that. Yeah. Oh, good idea.
So there's this triple Diffie-Hellman construction used in the signal protocol, noise, and OptLS that combines two long-term static keys with two ephemeral keys. And given that problem with static keys, is there anything you can do with those combinations of keys to kind of get the same thing where you authenticate through the static keys?
So if I remember correctly, you do 3 Diffie-Hellmans and then you basically concat them all together, right? You would have to solve this hidden isogeny problem for all of them, for all of those keys, and they're all public. So maybe, like, I think that would be a problem. I think so, but I don't think anyone has specifically looked at that construction yet. Yeah. Oh, sorry.
Gonna run around.
I'll let him choose.
So what kinds of proofs of security have there been for this? Are there any problems this has been reduced to, and what do we get out of that?
The third paper that I linked there is the best coverage of the proofs of the security of the problem. It basically reduces to the decisional supersingular isogeny Diffie-Hellman problem and the computational supersingular blah, 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 blah. You get it. Like that is the best paper. They will probably be able to describe it in depth for you. They have proofs. They have like security models and Oracle models that they, try to use in their proofs. So I think that's what would answer your question best. Yeah, what's up?
So I want to come back to the first question. Is there a risk that there are many easy to compute maps between two curves?
There might be, but you have to find the one. There can be many elliptic curves. There can be many isogenies between two curves. You're trying to find the right one with the right degree. And in this case, composed together of all of these small degree isogenies. So it's possible, but as far as I know, that's not like what is actually like considered a threat to the problem.
Okay, we'll do one more question, and then it's up to the next speaker. Who would like the last question? All right.
When you described an isogeny, I didn't notice anything that you mentioned that's different from just a normal homomorphism. So
it is a homomorphism.
Okay.
Yeah.
I was wondering if the
it's just for elliptic curves, they are called isogenies for some reason. That's all. Yeah. Like it's just a fancy word for a very common mathematical thing.
Okay, everybody thank Deirdre. That's awesome. My favorite thing about supersingular isogeny Diffie-Hellman is that these curves are just absolutely useless for regular Diffie-Hellman, and we finally found a use for them. Okay, so for our next speaker, Maya Kazarowski is going to talk about encryption at rest. Here you go.
Thank you. I think you can hear me. Yes. Brilliant. My name is Maya. I'm a product manager at Google. I focus on encryption at rest, encryption key management. If you're familiar with our cloud, I work on cloud KMS, customer supplied encryption keys, secret management, and then internally, which is much more exciting, I work on how we encrypt data at rest at scale, our crypto library, and I have the privilege of talking to our post-quantum crypto team, our secure computation team, our privacy set intersection team, all kinds of stuff like that, which is really fun. I don't work on encryption in transit, so I can do my best to answer your questions, but I'm not an expert on that. So what am I talking about today? So you can think about encryption as being a couple different things. This is the crypto meetup, so hopefully I'm not teaching you anything at this point. We're talking about encryption in transit. Encryption in transit is really about how you protect your data when it's stored at rest. So you're protecting it from a potential attacker stealing that data like on a disk, on your phone, from your email, whatever it happens to be. You can also think about encryption in transit. Encryption in transit is how you encrypt your data before sending it, authenticate both endpoints, verify that the two endpoints are supposed to be talking to each other and decrypt that data. What we do at Google uses HTTPS by default. We use 2048-bit certs. We use perfect forward secrecy. We have our own CA. We encrypt data in transit as it moves on our private network. Between our data centers, all our PCs are encrypted. So there's a lot already done in that case, and that's really about protecting data in case it's intercepted, in case somebody who shouldn't be seeing that message manages to get hold of that data. To what Deirdre was talking about earlier, or somebody could just store lots and lots of data and then potentially get to it later. That's why we use things like perfect word secrecy to protect that data. And the last point here is something that's a bit newer, encryption in use. So this is about how you protect your data when it's being computed upon. So you can think about, we typically here assume an honest but curious model, so that the server that's going to do the computation will actually do the computation accurately, but that you don't trust them in looking at your data. So you still want the privacy of that data. There's some research being done in this space at IBM around homomorphic encryption, like Craig Gentry's scheme. Google does do research in this space. Specifically, we have a open source experimental encrypted version of our BigQuery client. It's kind of like Amazon's Redshift that you can play with on GitHub, and I'll put the link up at the end. So we do research in this space as well. We're also doing research into like enclaves and that kind of stuff. All right, so let's focus on, I went backwards. Let's focus on encryption at rest. So everything I'll be talking about today is actually things that we've published publicly before. We're very transparent about how we do this. There's a white paper, there's a link right here. I also tweeted it about an hour ago. So if you're interested in reading a bit more about what I'm talking about today, it's all public. So please do take a look. Specifically, everything I'm talking about applies to Google Cloud Platform. And I'll be calling out anywhere that it does or doesn't apply to other products as well. So first off, we encrypt data at many, many layers. So you can think about kind of your traditional stack that you might have. Typically, what I'll be talking about is encryption at the storage layer. So you can think about encryption either in our distributed file system or at file storage. We encrypt data almost always at either the distributed file system layer or the file storage layer. And what that means is that the storage systems that Google uses, there are many storage systems depending on the use that you have, kind of like how when you go to a cloud, you can pick which storage system makes the most sense for your use case. We've built encryption by default into all of those storage systems. So our developers internally don't have to think about how to implement encryption, how to generate a key, if they should be encrypting this data or not. It just is encrypted. We've optimized it centrally. We've taken care of all of that, so they don't have to worry about it. They have to do it whether or not they think about it. We also encrypt data at the device layer. So I'm talking about like hardware devices. So we encrypt all new hard drives with at least AES-128 and any SSDs with at least AES-256, again, by default, throughout our whole fleet. So we don't want to rely on only one layer of encryption. We have multiple layers of encryption in place to make sure that if data is compromised at rest, it's protected. So I'll focus a bit more on how we encrypt data at rest in the storage system. So the first thing to note is that Google Cloud Platform encrypts customer data stored at rest by default without any action required from the customer using at least one encryption mechanism. So that's what I'll be talking a bit more about today. So to understand how we encrypt data at rest, you have to understand how we store data at rest. So when a piece of data is uploaded to Google, a YouTube video, an email, whatever it happens to be, we split that data into smaller chunks. A chunk could be up to several gigabytes in size. Each of those chunks gets its own locally generated data encryption key. And those chunks with their data encryption keys are distributed across Google's storage infrastructure. Notably, this is also done in backups. So we don't decrypt data and then re-encrypt it for backup. We just back it up already encrypted. In fact, the storage system, the backup storage system, will add another layer of encryption just to be safe. So the other important thing to note here is that each chunk of data is encrypted with a unique locally generated data encryption key. That data encryption key is unique to that chunk, even if that chunk is part of the same object as another chunk, even if it's sitting on the same machine as another chunk or the same data center as another chunk, even if it's owned by the same customer as another chunk of data, it gets its own uniquely randomly generated data encryption key. That's a pretty big deal. That's not something to think lightly about. How do we access data to these things? So each chunk will have its own ACL. So it'll have its own access control list of who has the right to access that particular chunk based on which object it belongs to, based on which storage system and which service is accessing that chunk of data. We also audit and log access to these things. So any individual or service that's on that ACL, any individual's access to a particular data chunk is logged and is auditable as part of Google's overall privacy and security story. Okay, so I've been talking about the data encryption keys that are locally generated, right? So you're thinking, okay, how do these data encryption keys stored? Well, typically we store these as like a header to the data, you can almost think of. So we store it with the data. What that means is that we can distribute those across Google's infrastructure and easily retrieve those pieces of data and the data encryption key when we need to. It also means that when we're backing up something, we back it up with its key. But nobody's going to write a plain text data encryption key to disk. No, that's a big no-no. So that data encryption key is encrypted with another key called a key encryption key. You might have heard of this as called envelope encryption. So I have a piece of data, it's encrypted with a data encryption key, and the data encryption key is encrypted with a key encryption key. Envelope encryption or key hierarchy is another way that I've heard it referred to. So a key encryption key is actually stored centrally in a key management service maintained at Google. This key management service is the same key management service for all our production services. So keys for Gmail, keys for Google Cloud Storage, keys for whatever are all stored in this central key management service. So I'm talking very fast. This key management service was built for this purpose. Keys are not exportable from that key management service. So what happens in practice is that a piece of data that's encrypted, in this case, a data encryption key that's encrypted, gets sent to the key management service. The key is used in memory within the key management service, and that data encryption key is sent back to where it came from. So that key encryption key does not leave the key management service. What that means is that we have the ability to audit every single time that key encryption key is used, and we know exactly who's accessing that as part of which job. Another thing to note is that we can, in the key KMS, rotate key encryption keys at regular intervals. So far I've been talking about keys as being like a single key, but in practice what we're talking about is a key set. So you can imagine that a key has a key rotation policy that says something like, generate a new key every X amount of time. For Google Cloud Storage, for example, it's every 90 days. So we'll generate a new key encryption key every 90 days. And we'll keep X amount of versions, old versions, still available and used for decrypting data. So for Google Cloud Storage, that's 20 versions. In practice, what that means is that we don't have to re-encrypt all of that data only every 5 years or so. I want to make a quick point here about key rotation. So we're talking about key encryption keys. You might be wondering, okay, what about data encryption keys? How are those rotated, right? Those locally generated random keys? We don't rotate those. What we do instead is generate a new random key every time you write data. So if you're only reading data, we'll not change it. But if you're going to write a new piece of data, edit that data in any way, we'll generate a new random data encryption key at that point in time. So at most, your data in something like Google Cloud Storage would stay with the same encryption key for roughly 5 years, 20 versions times 90 days. In practice, it'll probably be re-encrypted much more frequently if you're actively editing, accessing that data. So I was talking earlier about ACLs on individual chunks. ACLs also exist on key encryption keys. What that means in practice is that a particular key encryption key, as I mentioned, that can only be used within the KMS, has an ACL that says which services have the ability to call that key and use it. In practice, these are storage services. As I mentioned earlier, we have several storage systems inside Google. A service, something like Gmail, would use many different storage services depending on what it's trying to do, right? Is it looking for global availability? Is it looking for redundancy? Whatever the storage system is being used for. And that storage system would have keys that's inside KMS that lets it access those chunks of data. So we have individual ACLs on each of those keys linked to those storage systems. And again, that's all auditable as part of Google's privacy and security story. So one of the things I want to talk about today was the fact that we can do this at scale at Google. So I mentioned earlier that this is all built in from the get-go, right? We built this into the storage system so that people don't have to think about it. We're going to take that decision and that thinking out of developers' hands so that they don't have to worry about security. Part of that also means that our KMS, our key management service, has to be incredibly available and globally redundant and extremely low latency. What that means in practice is that we have tens of thousands of instances of our KMS running in our data centers globally. So no matter which service is running at Google within a data center, can go call this KMS that's running somewhere close by and get a key and decrypt that data, rather than the alternative of not encrypting that data to have lower latency. We've taken that, again, into consideration from the get-go. So what happens in practice? Oh, there's a weird, that's fine, we'll ignore that. What happens in practice? So I mentioned earlier that you can think about having a service, something like Google Cloud Storage or Google Compute Engine. You have a storage system, which are internal storage systems, but in essence, Google Cloud Storage is an externalized version of one of those. And then we have our KMS. So you have three actors in this chain. So the storage system says, hey, I want to access that email, that video, that piece of data, that file. The service does that. It talks to the storage system, says, give me that email. That email might be in 25 chunks, let's say, right? The storage system has to then go find which chunks of data that email is sitting in, pull the data encryption keys that is with those chunks, and pass those encrypted data encryption keys to the KMS. When the storage system did that, it verified that the service had the right to access those chunks. The KMS then says, okay, I have these chunks of these data encryption keys that are coming from the storage system for these particular chunks. Is the storage system authorized to use those keys? Do those keys correspond to those to decrypting those data encryption keys? And also, which job is running and asking for this? So Google has a concept of every service has an identity that's given at boot time, and we use that to verify and authenticate requests that are coming between services. So it's asking, okay, are you actually allowed to be doing this right now? Yes, you are. Great, let's do that for you. Then in memory, it decrypts that data encryption key using the key encryption key that's sitting in the KMS and passes back the decrypted data encryption key. Again, it's staying within a Google data center. It's going between Google data centers. It's on RPC that's encrypted and passes it back to the service. Then depending on which service, depending on which storage system, either the storage system or the service will decrypt that data chunk and pass it back to the service. So it's not always consistent in every scenario, but that's the general flow. There are obviously some exceptions for things like SSDs that have locally generated random keys, but this is generally what happens when data is being accessed at Google. So you're thinking, great, I have key encryption keys that are sitting in memory, but wait, how are those key encryption keys protected, right? So we have data is protected by data encryption keys, data encryption keys are protected by key encryption keys. You guys, it's turtles all the way down. Okay, so blue data, yellow data encryption key, green key encryption key. That key encryption key is sitting inside KMS. KMS is running in memory. KMS is running in tens of thousands of places in Google's data centers. KMS has something called a Kms Master Key, which encrypts all the things that are in KMS when they're sitting on disk. Again, we're not going to write keys unencrypted to disk. So Kms Master Key, where does that sit? That sits in something else called root KMS. And that's also running only in RAM. This is actually running in special security hardware in Google Data Production Fleet. It runs only in our data centers, only on certain machines in each data center that are running other critical security infrastructure. And it has a handful of keys. You can imagine some of our other extremely high profile things for signing things that we might want to keep there. Root KMS has its own root key called the root Kms Master Key. The root Kms Master Key is, again, kept only in RAM. The root Kms Master Key is distributed throughout Google on the same machines, the same security machines in our production fleet, through a peer-to-peer infrastructure that we'll call the root Kms Master Key distributor. So what happens is when a new instance of the root Kms Master Key distributor, this is what's fun about not having to use internal names, super long external names, it spins up and it says, okay, what are all the other hosts that are running the root Kms Master Key distributor? And it gets a list of those hosts and it says, hey, I'm a new version of the root Kms Master Key distributor. Give me the key. And they authenticate and they verify and then they give it the key. And now there's a new version, there's a new instance of the root Kms Master Key distributor. So what that means in practice is that as long as there is a single data center belonging to Google that's up somewhere in the world, we have a version of the root Kms Master Key in RAM. And that's kind of good enough for like encrypting all of our data, right? I don't know if we can handle all the load, but that's good enough for encrypting all the data at that point in time. Okay, what if every single Google data center at once globally were to go down? What a great question. So we're going to store that root Kms Master Key on, again, special security hardware in physical safes in 2 globally distributed Google locations that less than 20 people have access to. And those people have access to it basically to be able to bring back up Google if we need to. So again, a quick summary. Data is chunked. Those chunks are encrypted with locally generated random data encryption keys. Those locally generated random encryption keys are data encryption keys, and those are protected with a central key management service. That key management service is managing key encryption keys, which are practically one or a couple per service. That KMS is running in memory in Google's production fleet. KMS is protected with a KMS Master Key, and the KMS Master Key is kept in root KMS, which is also running in memory. This is running on specialized security machines in Google's production fleet. Root KMS is protected by the root KMS Master Key, and the root KMS Master Key is distributed in a peer-to-peer infrastructure in Google's, again, security machines in our production fleet. And if everything were to go down, and if everything were to break, and there was a volcano that stopped all of our, our own fiber from talking to all of our other data centers and they all lost power at once and real bad things happened. We have a copy, multiple copies of the root Kms Master Key sitting on hardware, security hardware in physical safes in 2 globally distributed Google locations. So that's how we think about key hierarchy at Google. So we're a little bit paranoid, which I think is great. Okay, so I've been talking a lot about our key hierarchy and how we manage all these keys. So that's what makes it possible to do it at scale. Another thing that makes it possible to do it at scale is the fact that we have a central cryptographic library. So you might have heard of Kezar. It's on GitHub. This is an old version of what we have internally. Do not use this in production, please. One, because of lots of dependencies, but also because we know that there are issues with it. Internally, we've patched that and fixed it. And the benefit of having a central cryptographic library is that people who aren't good at crypto don't have to think about crypto. People who can't implement crypto don't have to think about crypto. We only need a handful of really, really good crypto people to review that library, patch it, update it. We're able to easily find every time an instance of a particular library is used in code in production, so that we know if there's an issue with a new crypto system or an old crypto system, that we can go find it and fix it. That's actually really, really, really helpful. So having a central key library, having a central crypto team has helped us incredibly to how we can manage encryption at scale at Google. So a quick summary here. We've encrypted many layers. I mentioned storage layer encryption, which is what I went into, but we also have disk layer encryption in terms of hard disks and SSDs being encrypted. For the storage encryption at many layers, we chunk that data. We encrypt data locally with data encryption keys, wrapped by a key encryption key centrally. We have a whole key hierarchy, and then we use a central cryptographic library to manage all of that. So I'm going to pause here and stop talking a little bit about Google and talk a bit about, okay, what if you're not at Google? What if you're not as big as we are? What if you're not using Google Cloud? How do you encrypt data at scale like we do? And what are some lessons learned here? The first one should be obvious to everyone in this room. Please don't roll your own crypto, please. The second one here is not doing a security review. So some of you might be familiar with CryptoCat. They had a known vulnerability in how they were generating keys that created a significantly smaller number of keys than expected. And they had that vulnerability for about 19 months or 18 months. And it was just found, like, it was a simple bug that was found. And the founder said something like, if we had done a security review, we would have found it. Yes, you would have. Please do a security review. The next one here, using multiple forms of encryption with different bits of security. This is a great one that I hear a lot, actually. People think that, hey, if I have, I'm going to put all the types of security on top of each other, and it's going to be even more secure, and I have this military-grade crypto. No. I think there might be an exception here if you're thinking about post-quantum crypto in terms of using things that you know are weak in different ways. I know Google's already starting to test the New Hope post-quantum algorithm in the Chrome Developer Edition. But the idea there is to be just future safe, not to provide additional security right now. The other fallacy there is that whatever the weakest layer you have is it's going to be what's going to break you in some sense, right? So, like, you know, using AES-120 and then using AES-256 doesn't give you anything additional. The next one here, using the wrong kind of thing to solve a problem. Encryption, hashing, data anonymization, data aggregation. These are all tools that we have at Google that we use for different things. They're all useful, but it starts to be a problem when you start encrypting data that you should be anonymizing, or deleting data that you should be aggregating, or something else, right? So, general rule of thumb: if you don't need the data, don't write it, and anonymize or aggregate what you don't need the details for. Leaving private keys in a public code repo. So if you searched GitHub, I want to say this is 2006, but I could be wrong about that. You would find 600 IDRSA files. I saw on like Hacker News, like maybe last week, you could do a search for all pull requests that had something like remove passwords. And I was like, okay, that's great. Let me go look at those. So please don't put things in a public code repo. What we actually do at Google, which is kind of cool, is we have some pre-submit tests that say, hey, that looks like an RSA key. Maybe you don't want to be doing that. So if your developers are going rogue, we'll stop them. Well, ideally, you can stop them. The next one here is using the same encryption for multiple items. So we talked earlier about chunking data and how we have a randomly generated key for each chunk of data. Reusing the same key would be equivalent to using one password for everything, right? There's no need for you to increase your exposure to risk in that way. The whole point of being able to have chunked data or different objects that you can actually encrypt them at scale. So there's no need for you to be reusing that key. The next one here, using a non-random number generation source or not using an IV. There was a bug. Oh, this is the 2006 one. There was a daemon bug in 2006 that took away OpenSSL's source of randomness, so it was only using the timer, which reduced the number of possible keys to about 64,000, which is brute forceable. I also saw a really great article maybe a year ago. I think it was a French startup that said something like, we're going to use lotteries as a source for randomness. And I'm like, okay, I agree that lotteries are not predictable, but lotteries are also using the source for randomness. So like, why don't you just use their source of randomness rather than using their output? It didn't really make a lot of sense to me. A quick thing to point out here, if you're using, I get asked this question a lot, if you're using Google Compute Engine, we give you direct access to the same randomness that we have internally. So you can call urandom or random and you'll get something good. And the last one here is only looking at individuals' access to data, not also keys or services. So I talked a little bit about logging earlier and how we want to manage access to keys and make sure that people aren't doing things they shouldn't be doing. Often when companies are investigating incidents or looking at how to manage access or looking at separation of duties, they're only looking at the data itself. Basically, you should be looking at anything that gives you access to the plain text data. So somebody has access to the keys and they also have access to the encrypted data, that's the equivalent, right? So make sure you're managing your ACLs and your auditing so that people don't have access to things they shouldn't have access to. And I think that's it. Here are a bunch of links. There's a white paper that explains most of this, a bit more about our security. And then I linked to Keyzar. Do take a look. Don't use it in prod. Encrypted BigQuery client, which is our partially homomorphic crypto experimental thing. And then there's a blog post on how we use A New Hope. Awesome, thanks.
Hello. We got some time for some questions, so raise your hand. We'll start here.
Hi. You mentioned a bit about the hardware you're using on your root master distributors, and could you tell me a little bit more about that, whether it's off the shelf, HSMs or Google built hardware, or if it's like CPU features? And
yeah,
also,
I think you're asking about a couple different things. So there's two pieces of hardware that we'll mention. This one. This is running in security hardware, and this is also on hardware inside a safe. Neither of these are HSMs; they're both custom built. Yeah.
So I have a question. You guys are storing all the keys and all the master keys globally. I guess it's more of an applied crypto question. What happens in, say, since we're on the topic on French startups, in France, where you have to give up all the master keys? So does that sort of present an unsettling question? You just copied all the keys all over the world, made it very highly available. All the master keys are global. Now under French law, they simply have access to everyone's data. So you just built the world's easiest, most sophisticated surveillance system where you got access to all the data in a single swoop.
Yeah, I'm not the right person to talk about legal implications or public policy, but it is the same set of keys globally. So we use one version of KMS, one instance of KMS that's running many times, the same copy of root KMS that's running many times, etc.
So you talked about the key rotation for like if you have a key encryption key that gets rotated every 90 days, you keep 20 copies, so you have 5 years of data. Is there a software level enforcement that data is touched every 5 years to avoid the situation where like, oh, well, this was put 5 years ago and we forget it?
Yeah, no, we wouldn't forget it.
So I mean, like, but is that enforced at like?
It would force like re-encryption of data.
Okay. One more. How often, like you talked about key rotation of the individual keys, what about something like the KMSs or whatever? Because you'd have to then re-encrypt all the keys at that level, right?
Yeah, so basically what happens is if you rotate the most root key, right, you'd only have to kind of rotate the next layer and so on. And key rotation is an interesting topic because people are like, oh, the best practice is to rotate your keys every 30 days. And you're like, okay, well, like, what are you protecting against? So like for our data encryption keys, as I mentioned, we don't rotate those. We just change them when we re-encrypt data. Key encryption keys depends on the service, depends on their risk and what they're trying to get. But basically what we're getting at is that it should be fairly simple across the whole stack to rotate a key like that if you needed to. If you thought there was a reason you wanted to change all your keys all at once, you should be able to do it.
Is the KMS available as a service?
So this KMS is not available as a service. There's another product called Cloud KMS that I'm the PM for also. And I can talk all about that if you want. Nick is running around with mics.
Two-part question. Yeah, two-part question. One is, I think the gentleman asked the same question. Can you describe a little bit more on your infrastructure for hardware root of trust? And second part is, how do you get assurance on the other hardware components on your hardware for things like firmware attacks?
Yeah, so we're asking about hardware again. We don't use an HSM. The security machines in our fleet are custom built. The security that's sitting in safes is also custom. Google is extremely picky about how its supply chain works. I'm not the right person to answer this question, but we don't use HSMs.
You mentioned that when a new distributor comes online, the other ones authenticate it and say, give me your key. That has to be based on a secret of some sort. Can you say anything about how the new machine gets a key that is then known to the other ones?
So I mentioned very briefly earlier that every service at Google, when it boots up, gets a unique service identity. And that's actually authenticated both the machine that it's on and a bunch of other things. Unfortunately, we don't have anything public about how we do that right now. I wish we did.
Hi. So you said the KMS they're replicated. But at the same time, the key that they protect are not exportable by design. So how do you replicate? Do you have like hardware assurance then?
Yeah, we push those as encrypted blobs. So the KKs would all be encrypted with the master key and pushed on disk, and then it would get opened up locally in memory.
Okay, well, thank you very much, Maya. Let's give another round of applause. So our last speaker of the night is Andrew Eyre, who is going to be speaking about certificate transparency. Andrew.
Thank you, Nick.
Let's give him a nice round of applause. Thanks, Andrew.
Thanks. So I'm Andrew Eyre. I'm the founder of SSL Mate, which is a company that helps people automate their SSL certificate deployments. I'm also the author of CertSpotter, which is a certificate transparency monitor. And if you don't know what that is, you will at the end of this talk. So many of you are probably familiar with certificate authorities and how certificate authorities are basically the trusted third parties which issue certificates which help us secure our connections to TLS servers. And over the years, certificate authorities have messed up a number of times. Here are some of the recent incidents. So Symantec, they issued some certificates for test.com, example.com, and other similar domains. The owners of those domains did not ask Symantec to issue these certificates. Symantec just issued them for their own testing purposes. The incredible thing about this is that a couple years ago, Symantec was caught doing the exact same thing. They fired some people, but they never actually fixed the root cause, which is why it happened again. We had some certificate authorities with domain validation vulnerabilities. Komodo was doing something quite astonishing, which is that they were using optical character recognition to parse email addresses from whois records. So like someone, who had an email address in their whois record, like maybe contained an L, they would parse it as a 1. So then someone could go and, sign up for that email address at, say, Gmail, and then they'd be able to approve certificates for that domain. Let's see, we've had a bunch of certificate authorities issuing SHA-1 certificates, which has been forbidden since the end of 2015. Symantec issued a certificate with a non-random serial number. That's random serial number is a mitigation against hash collision attacks. And they basically did that intentionally because a customer asked them to. Then Verizon, they issued a bunch of sub-certificate authorities, and they forgot who they issued those sub-certificate authorities to. DigiCert then bought the Verizon Certificate Authority business, and DigiCert basically has no idea what they bought. And then WoSign and Starcom, well, I mean, there were so many issues there that Mozilla had to create a special wiki page, assigned like each issue a code from A to Z, and And these are just incidents that happened in the last year. If we go back, farther, the list starts looking more like this. So
anyways, this just isn't acceptable at all for a system, which, the entire security of TLS, rests upon. That we really have to do something about this. So Justice Brandeis, who was a Supreme Court justice, said, sunlight is said to be the best of disinfectants. And what he means is that transparency, can help, improve things. So some folks at Google, Adam Langley and Ben Laurie, had this idea a few years ago to apply this principle to the certificate authority system. So they said, well, let's set up some logs and let's put every single publicly trusted certificate in these logs. And then we'll let people query the logs. So people can look through these logs for bad certificates. So for example, if you're the owner of example.com, you can look through the logs and you can say, hey, wait, this semantic certificate for example.com, I didn't ask for that. Or you can look through the logs for SHA-1 certificates or other misissued certificates that certificate authorities shouldn't have issued. So certificate, this doesn't actually directly stop certificate authorities from doing bad things. However, it makes their misissuances detectable. And there are several advantages to making misissuances detectable. One of them is that it allows us to remediate the incidents, because obviously if you don't know that something bad happened, you can't remediate it. This could include revoking certificates to the extent that revocation works. It could also, in the extreme case, mean distrusting the certificate authority, which is what happened to WoSign/Startcom. And that in turn encourages better certificate authority behavior, because obviously if you're a certificate authority, you don't want to be distrusted. And if you know that if you do something bad, it'll be detected, that means that you're going to be incentivized to do a better job. And then the data we get from certificate of transparency better informs, our efforts to improve the security of the web PKI. And finally, I want to say that one big advantage of certificate transparency is that it doesn't burn the existing system to the ground. It's quite difficult to replace a system that already has wide deployment on the internet. Just look at, for instance, how long it's taken us to roll out IPv6, and that is still ongoing. Certificate transparency, on the other hand, that has been around for just 4 years, and already, we have wide deployment of it, and that's the advantage of using a system that can be layered on top of what you already have. So it's not quite enough to just put these logs and put certificates in these logs. We have to make sure that clients will only trust a certificate if it's actually been logged, because otherwise a certificate authority will just not log any certificate that they misissue. So the way this is accomplished is with something called a signed certificate timestamp, or an SCT. What this is, it's a signed statement by a log promising that it's going to publish a certificate. So when you submit a certificate to a log, the log replies with this promise saying, I am going to publish this within the MMD, which for all logs is currently 24 hours. And then the clients will only trust a certificate if it's accompanied by SCTs saying that it's going to be published in some log. So since a client will only trust a certificate if it has SCTs, we need some way to tell the client about those SCTs. There are 3 ways to do that. The most conceptually simple way is to use a TLS extension. With this, it's the responsibility of a server operator to submit their certificate to some logs, get back the SCTs, and then configure their web server software, like say Apache or Nginx, to serve back to the client the SCTs. This requires server support, and presently not many servers have support for this. So this is why we have another option, which is to use an extension in OCSP. In this case, it's the certificate authority's responsibility to log the certificates. They will take those SCTs that they receive from the log, and they will embed them in the OCSP responses for that certificate. Then the servers will retrieve the OCSP response and staple it. Now this is better than the TLS extension in that it doesn't require special server support, and it doesn't make it the responsibility of the server operator to log. It does require OCSP stapling. That is more common than support for the TLS extension. However, not everything supports OCSP stapling, and many of the implementations for OCSP stapling are not very robust. So this is not a universal solution. The final solution, the final way to deliver SCTs to clients is to put them inside the certificate using an X509 extension. So in this case, the CA is responsible for logging the certificate. It takes the SCTs that it gets for logging and just sticks them inside the certificate. And this works everywhere because you don't need any server support. You just configure your certificate as normal, and the SCTs are delivered to the client inside that certificate. The downside to this approach is that you can't change the SCTs that are inside the certificate once the certificate has been issued, which means that if a log goes out of business, that means that the SCTs issued by that log, are no longer going to be trusted. If you're using the TLS extension or the OCSP extension, you can always just log your certificate to some other logs and use those SCTs instead. In the case of the certificate extension, there is a risk the certificate will become distrusted. Now, you can mitigate this by embedding, multiple SCTs from many different logs inside the certificate, so you have some fallback if one of them becomes distrusted. And now there is a bit of a chicken and egg problem here, because in order to log a certificate, you need to sign it first. But in order to sign the certificate, you need to have the SCTs inside. So we solve this using a layer of indirection called pre-certificates. And in that case, a pre-certificate is basically just a surrogate for a certificate. What the certificate authority does is it signs the pre-certificate, then it logs the pre-certificate, takes the SCTs that it gets for logging the pre-certificate, puts them in the final certificate, signs, and issues that. Yeah. So, as I've described certificate transparency so far, we've got a bit of a problem, which is that we're putting a lot of blind faith in certificate transparency logs. And there are a few ways that a certificate transparency log could violate our trust. It could issue an SCT. It could say, I promise to log the certificate, but then it could just never log that certificate. And that's bad because it's put out the SCTs. It means clients will trust it because the clients think it's logged, but no one can actually see the certificate because the log doesn't log it. The log could remove entries from the log, or it could present different versions of the log to different people. So this is just not good enough because we don't like trusted third parties. The certificate authority system is an example of trusted third parties, and look at how terribly that has turned out. So we solve this using something called a Merkel tree. So the naive solution to this would be for every TLS client everywhere to maintain its own, to store a copy of the entire log. Because if the client has a copy of the entire log, it can verify that a certificate is in the log. It can verify that when the log adds entries to it, it's not removing any entries that were already there. This, of course, is completely impractical because obviously we can't have every TLS client everywhere storing a copy of every certificate ever issued. So this is where the Merkel tree comes in. So we start out with our certificates 0 through 5 that we want to put in a log. Then we take the hash of each certificate. So A is the hash of 0 and so on. These hashes form the leaves of our tree. We then take pairs of these hashes and we hash the pairs together. So the concatenation of A and B, we take that and we hash it and we get the hash I. We do this recursively. And then finally, we take the remaining two tree nodes, we concatenate their hashes, and that forms the tree head. The log then signs this tree head. It signs the hash along with the size of the tree 6, and that signed statement is what's called the signed tree head. It's a statement saying that at size 6, the tree had this hash. And now clients don't need to store the entire log. Instead, clients just need to store the latest signed tree head for every log, because the information in the signed tree head, the hash of M and K, that in turn ultimately contains the hash of every certificate. So let's put this information to use. The first thing we might want to do is a client has seen an SCT for certificate 2. Now this SCT is a promise from the log saying, I promise to publish this certificate in the log. So the client now wants to challenge the log, say, okay, show me proof that you actually put certificate 2 in your log. The naive way to do this would be to query the log and have the log return certificate 0, 1, 3, 4, and 5. Then what the client would do is would take 0 and 1, hash those together, take 2 and 3, hash those, and 4 and 5 and hash those, and so on, and reconstruct the root. And if the hash that the client has reconstructed matches the hash which the client already has on file for that log, that means that certificate 2 has been included in the log. This, of course, is very inefficient because the log has to return every other certificate it has. But looking at this tree, we can actually skip returning some of this information. So for example, instead of the log returning 4 and 5, the log can just return the hash k, because the client would just have hashed 4 and 5 together to get k anyways, so we can just save some data and the log can just return k directly. Same thing over for A and B. Instead of the log returning 0 and 1, the log just returns I. And finally, the log would return D. So now what the client does is it can hash 2 to get C, concatenate C and D to get J, then it concatenates J with I to get M, finally concatenates M with K. The client then reconstructs the root, and if that matches the root which the client already has on file for the log, it means that certificate 2 is indeed in the log. All right, so now let's talk about adding entries to the log. So the log gets 2 new certificates, 6 and 7. What the log is going to do is it's going to concatenate the hashes of 6 and 7 together, form hash L. Then K and L will be concatenated, hashed to form N. And then we'll take M and N, and we'll now create a new tree head of size 8, which ultimately contains the hashes of certificates 0 through 7. Now, the old signed tree head of size 6 is no longer actually part of this tree, but it was at one point in the tree head, which is why I'm leaving it on the diagram with these dotted lines. So now the log is going to publish that it has a new signed tree head of size 8, and it has this root hash. Clients need to verify now that this new STH is consistent with the old STH. And consistent means that it's an appendage, that the new STH, that the tree represented by the new STH is an appendage of the old tree. That is, it contains all the certificates that the old tree had, plus some new ones. This is how we ensure that logs are not removing old certificates or editing them. And so naively, the way we would do this is that the log would return all of the certificates that were in the old tree. That would be certificates 0, 1, 2, 3, 4, and 5. The client would then hash them together, make sure that those certificates still match the old tree head that the client had. Then the client would hash together the new certificates and make sure that those, along with the old tree head, form the new tree head. But we can do that more efficiently. Specifically, we can just have the log return M, K, and L, because the client could then take M and K, hash those together to get the verify that matches the old signed tree head. Then it can take K and L, hash those together to get N, take that with concatenate with M and hash, and verify that yes, now this does match the new signed tree head, and the client can be assured that this new tree head is consistent with the old one. Now, nice thing about these proofs is that the size of the proofs increase logarithmically with the size of the log. So for example, with the inclusion proofs, if the log has 2 to the n certificates in it, the size of the inclusion proof is going to be only n. And this is great because it means that we can have a certificate with 4 billion, we can have a log with 4 billion certificates in it, and the inclusion proofs are only going to be 32 hashes long. So there are 32 SHA-256 hashes, so that's very little data. Yeah, so let's talk about certificate transparency today. We've got an RFC 6962, that describes how certificate transparency works. This is an experimental RFC. There are 24 logs which implement this RFC. 11 of those are trusted by Chrome. The others are special purpose logs or logs that are currently or were formerly pending qualification by Chrome. Google operates 8 of these logs. Venafi operates 2. Chinese company Pu Chuang Saida operates another. And then NorduNet, which is a collection of Nordic educational institutions, operates a log. And then the rest of the logs are operated by various certificate authorities. Generally speaking, the logs which are operated by non-certificate authorities accept any publicly trusted certificate. So if you have a certificate that's trusted by some browser somewhere, those logs will accept it. The logs that are operated by certificate authorities, on the other hand, generally only accept certificates that certificate authority issued. And in some cases, these certificate authorities will let other certificate authorities log if they have a reciprocal agreement, like say, we'll let you log your certificates if you let us log ours in your log, or if the other certificate authority paid them a fee for the privilege of logging. And the reason for that is that it does cost a lot to run a log, and certificate authorities don't necessarily want to be helping their competition out, so they run these more selfish logs. In total, there are 91 million unique certificates across all certificate transparency logs. The largest log, which is operated by Google, has 75 million certificates in it, and it's growing by about 13 million a month. But of course, that rate is itself accelerating, so these logs are just growing very fast. Now, we've had some log failures. There was a log operated by a company called Certainly. They had too much downtime. They had less than 99% downtime, and Google Chrome requires at least 99% over 90 days. Problem with a log that's down a lot is that no one can access that log to see what's in it, so Chrome kicked them out. Izempe, they used the same private key for their test log and their production log. And what this meant was that basically every single STH they issued was inconsistent, because the problem was you couldn't tell if an STH was from their test log or their production log, and if you tried to get a consistency proof, it would just fail. So they were given the boot immediately. Aviator, that's one of the Google logs. There were so many certificates being issued to it that Aviator could not incorporate all of them within their 24-hour maximum merge delay. So Aviator issued these promises, we're going to log the certificate within 24 hours, but they didn't. It ended up being like a few hours over. So Chrome kicked out a Google log because of that. And then finally, now this is very exciting. This is breaking news. I'm sure that many of you were aware of the S3 outage today. Well, Venafi went down during the S3 outage. This by itself is not a big issue, because as long as they remain above 99%, they'll stay in. But shortly after S3 came back up, I got an alert from my monitor that a consistency proof failed. What seems to have happened is that right when the outage began, they issued a signed tree head saying that certain certificates were in the log, but they then forgot about those certificates. So when they came back up, they issued a new signed tree head, and this new signed tree head did not cover certificates that was in the old one. So they violated their append-only property. I reported this. There's probably going to be some discussion, but I suspect that Chrome is going to kick them out, because once a log misbehaves, you really can't trust it at all from that point forward. So I think they're going to be like Izempe and be kicked out. So that's very exciting. All right, so let's talk about client and browser support. So Chrome requires that all extended validation certificates be logged. They've required this since about 2015. If an extended validation certificate is not logged, Chrome will treat it like a normal non-extended validation certificate. Chrome requires that all semantic certificates issued since June 2016 be logged. I wonder why. And they're going to require that all new certificates be logged starting October of this year. Now, Chrome relies exclusively on signed certificate timestamps. It does not do inclusion proofs yet, which means that a log could lie. Say it's going to promise to log a certificate. Chrome will trust that certificate, and Chrome will never actually detect that the log failed to follow through on that. They are working on fetching inclusion proofs over DNS. And the reason why they're fetching them over DNS instead of contacting the logs directly is because there's a privacy leak with this. Because if you ask a log, show me a proof for this SCT, the log knows what certificate that was. The log knows what website that certificate is for. So the log knows what websites you've been visiting. By fetching these proofs over DNS, the theory is that these DNS requests will all sort of be aggregated together by your recursive DNS server, combined with a bunch of other people's inclusion proof requests, and that should provide some privacy. Google's interim solution for this is to require SCTs from both Google and non-Google logs. And the rationale is that they can trust Google logs. They can trust that Google logs are not going to lie, and that Google logs will actually incorporate all the certificates that are logged. Of course, that wasn't true for Aviator. Aviator took too long, although Aviator did eventually incorporate all the certificates. But that is just a short-term solution. Their long-term plan is to get the inclusion proof fetching, and then they will not require SCTs from Google logs. Now, Apple has very preliminary support. If you're an app developer, you can use App Transport Security to opt in certificate transparency enforcement for certain domains. The documentation is very poor on this. We don't actually know what that means. All they said is that it requires SCTs from at least 2 logs, but they don't say what logs they trust. You can do a deep dive into the code that they've open sourced, but that code isn't even up to date. But this is going to get better. So you can expect, some better documentation from Apple in the hopefully near future. Mozilla has started discussions on how Firefox will support certificate transparency. They do have some concerns about log auditing, how they're concerned about how they can actually ensure that SCTs are being followed through upon. And Microsoft has not announced anything. However, they were present at last week's Certificate Transparency Policy Days that Google hosted. So I'm going to take that to mean they are interested in perhaps doing something with certificate transparency. Let's talk about monitoring. So logs are basically just really long lists of certificates, and there are a lot of them in there. Monitors take those lists and do something useful with them. For example, monitors might take all the certificates and index them by domain name, or the monitors might send you an alert when someone issues a certificate for one of your domains. So some of the monitors out there include CertSpotter, which is the monitor that I wrote. CertSpotter is really good for alerting. So there's an open source project. You can download that, install it. You put all of your domains inside a file, and then you have cron run CertSpotter once a day or once an hour or however frequently you want to run it. And if it sees any of those domains that you put in the configuration file, it will send you an email. If you don't want to run it yourself, there's a hosted service that I run that's free for up to 5 domains. Then there's crt.sh. That's pronounced search. It's by Rob Stradling of Komodo, who is also a notorious pun maker. It's very good for searching. And yeah, ever since it was launched about a year and a half ago, anytime there's been any sort of certificate authority misissuance, the discussions on Mozilla's mailing list about it they're just full of search links. So it's been a very valuable resource in the web PKI. Facebook has a monitor. It's actually integrated in with the rest of Facebook's notifications. So you'll get a friend request, and then you'll also get a message saying Symantec issued a certificate for one of your domains. Google has a page which you can go to look up all of your certificates. And then DigiCert has a monitoring product also. So let's talk about the future of certificate transparency. So the IETF is working on a standards track version of certificate transparency, currently called 6962 BIS. This is just contains some minor improvements to RFC 6962. It's mostly the same. It's currently in working group last call. It's been in this about 3 times. Hopefully, it will actually make it through soon and go to publication. The IETF is also working on some other internet drafts. It's working on one for Gossip. Gossip helps with auditing logs because, for example, you might want to gossip sign tree heads. Because if a log is presenting different views to different parts of the internet, you want one part of the internet to be able to say, I saw this STH. Gossip that with someone else. And then if that someone else finds that that STH is not consistent with the STHs it has been observing, it can raise the alarm that this log has misbehaved. It also contains some ways, some alternative ways to get inclusion proofs that don't require the DNS approach. Then there's also a thread analysis internet draft. There's some talk about making a log monitor API. So this is something that CertSpotter and Search would implement. And then there's been a lot of talk about redacting sensitive DNS labels. If you're a big company, you might have some subdomains that you would rather not be publicly known. For example, you're working on some secret project, and you are running that at secretproject.example.com. If this gets logged in certificate transparency, your competitors know that you're working on the secret project. So the proposal here would be that instead of logging a pre-certificate for secretproject.example.com, we would log pre-certificates for questionmark.example.com or something like that. And this way, the owner of example.com can still monitor for their domains, but they do not see the full host name. This is rather controversial because in many ways this undermines the goals of certificate transparency because we're no longer logging the actual certificate, we're logging a redacted version of it. So we'll see what happens there. So far, Chrome hasn't been very enthusiastic about supporting that. And then finally, there are some efforts underway to take the same principles of certificate transparency, namely the Merkel Tree and public auditability, and apply them to other contexts. Binary transparency, that's a way for you to log software, basically, software binaries. So you can be sure that you have the same binary as someone else, not, say, a backdoor binary. And finally, key transparency. That is like certificate transparency, but for things like PGP keys or maybe signal keys or keys that might be used for encryption in Gmail at some point. Right. So that's all I've got on certificate transparency. Are there any questions?
What are some proposed mechanisms for gossiping the STHs?
Okay, so gossiping of STHs is called STH pollination. The idea here would be that websites would have a special endpoint hosted under .wellknown. It would be .wellknown/ct/STH pollination. And the idea would be is that if you've observed some STHs and you would then just take those STHs, post them to that endpoint on someone who's willing to accept them, they would then return the STHs that they've seen, and so that you can then verify the consistency between them. Does that make some sense? It's not really a very clever system, actually. It's really just like a JSON endpoint that we run. Well, it's not really centralized in that anyone can run one of these endpoints and you can gossip to all of them instead of just one, but there is going to have to be some place where you find out, who's doing this, and so it is centralized in that regard.
Any other questions? Oh, down back at the back.
Other than leaking things like secret project or other domains that an organization that may have been logged a certificate to the transparency log, what other abuses or threats have you seen to these CTs?
So do you mean threats against websites which have logged or threats against the ecosystem in general?
Both.
All right. Well, I think probably the only threat to people who have logged would be the discovery of host names, which are otherwise not public. That could be, for example, host names of internal servers. That could be used by an attacker to map out a network before they attack it. In terms of the ecosystem, I think the biggest risk is probably in denial of service against logs. Because these logs, they have strict uptime requirements. And if someone manages to send a DOS against them, that'll take them down, and then they'll be distrusted by Chrome and other browsers potentially. There's another risk that someone could log private data to these logs. So Europe, for example, the European Union has a right to be forgotten law. What if a certificate contains some personal data, like it could, instead of a website certificate, it could be an SMIME certificate containing a person's name. Someone would like this to be removed from the logs under the right to be forgotten. What does a log do then? Because it can't remove an entry without violating the append-only property and causing inconsistent STHs to be offered. So really the only option it has there is to just, be taken down.
Or you find a SHA-1 collision.
Oh, well, yeah. I mean, fortunately, we're using SHA-256 in certificate transparency, but it wouldn't be so good if SHA-256 were broken. Not just for CT. I think internet would be pretty hosed if that happened. So let's hope that doesn't happen.
Just a second, in the front.
So last I checked, the only SCTs that Google includes for their own, like Google.com cert, were a Google log, I think Aviator, and Vanafi. So if Vanafi isn't trustworthy, any ideas what they're going to replace it with?
Well, so just to make sure I understand the question, what Google for their own certificates logs to one of their logs plus Venify, and question is, what's going to happen to those certificates if Venify is given the boot? Is that right? Okay, so the Chrome policy has sort of a mechanism in there where it says that in the case, so I guess first of all I should say that in the case of OCSP and the TLS extension, because remember there are three ways to deliver SCTs: the OCSP extension, the TLS extension, and inside the certificate. If they're using the OCSP or TLS extension, they can always get SCTs from somewhere else. Of course, I guess the problem there is that perhaps there aren't any other logs willing to accept their certificates. Fortunately, it's not yet October 2017, which means that their certificates would not be distrusted. And if it were after October 2017, things get more complicated.
Isn't Chrome's policy that if the log was valid at the time of issuance, when it's inside the cert, it still works?
Yes.
So I think you should be fine for the existing Google certs, right?
So nothing bad is going to happen to Google certs. And yeah, as Nick was saying, if for the third mechanism of delivering SCTs, which is embedded in the certificate, Chrome requires that at least one of the SCTs be valid at time of check. The log must be trusted at time of check. The other SCTs, however, only needed to have been trusted at time of issuance. It's actually a rather complicated policy, but the goal is to not leave certificates distrusted unless all of the SCTs go bad.
One more question.
Are there any policies or checks around the logs ensuring storing of the actual certificate data? Specifically, like when you mentioned the right to be forgotten thing, the Merkel Tree system only ensures that the log has received the certificate and hashed it once. So they could actually run a perfectly valid log, only ever storing the hashes of the certificates, which would mean you'd have something that ensured it had been seen, but could not actually ever be queried. So are there any checks that Google does around the ones it trusts beyond simply ensuring that certificates are getting in there?
Yes, so Chrome policy requires that logs implement RFC 6962, and one of the endpoints defined by RFC 6962 is the get entries endpoint to return all of the certificates. So a log that doesn't store the certs just issues STHs and consistency proofs and inclusion proofs. That would not be compliant with RFC 6962 and therefore not pass Chrome policy. In terms of actual technical checks to ensure that a log is doing that, no, not like there's not proposed that TLS clients would like make hits to get entries. But you know, if some like say I run a monitor, if some log doesn't let me get the certs, I'll go complain on the certificate transparency policy mailing list, say this log is not in compliance, do something about it. Okay.
Okay, everybody, thank Andrew.
Right, thanks.
Well, that's it for our lineup tonight. Feel free to hang around for a bit, chat with other folks interested in crypto, and thanks again for coming to Cloudflare.